Principal and shear stresses in a gravity dam. In a gravity dam, consider a small element on the downstream face of the dam. This is ABC element in which this angle is 90 degrees. Say this angle downstream face making an angle with the vertical is alpha, then this angle will be alpha, and this will be 90 minus alpha, and this also will be alpha. So this is our alpha. On the downstream face, say water is up to a height of h dash, then pressure due to water, the triangular variation, say the pressure is capital P dash, then P dash acts normal to the face AC, so this is P dash. Then the length of AC, let us take it as ds, and length of BC, let us consider it as dB, and AB let us consider it as dr. On BC face, shear stress acts, that is say tau, and P max acts on BC face. When we consider the pressure distribution, maximum pressure will be at the downstream face. This is a maximum pressure, and minimum at the heel portion. So P max acts on BC, and AB will be say sigma. Since on AB and AC faces no shear force is acting, so these two faces will be principal planes, and the stresses acting on them will be principal stresses. Now considering unit length of the dam, then force acting on AB face will be sigma into dr into 1. Then force acting on AC will be P dash into ds. On BC it will be P max into dB, and tau also is acting on dB length phase, so into dB. So this angle is alpha, then this angle will be our alpha. Here with the horizontal it will be alpha. Now taking components along horizontal direction and vertical direction, first let us consider vertical direction components and equate it to 0. Sigma into dr into its vertical component is cos alpha. It is acting downwards, so let us consider it as negative. Due to P dash it will be downwards, negative. P dash into ds into its component will be sine component along the vertical, which will plus P max into dB. Equating it to 0, sigma dr cos alpha will be equal to P max dB minus P dash into ds into sine alpha. Dividing by dr cos alpha, sigma will be equal to P max into dB by dr cos alpha minus P dash into ds sine alpha by dr cos alpha. We know if this angle is alpha, then dB by dr, since this length is dB, this is dr, and AC is ds, then if this angle is alpha, dB will be our adjacent angle, so the hypotenuse by adjacent side will be equal to secant alpha, so that is secant alpha. Substituting P max into dB by dr is secant alpha by cos alpha minus P dash into, from the right angle triangle, ds by dr. Our ds is opposite angle by dr is adjacent angle, which will be equal to tan alpha. Substituting tan alpha into sin alpha by cos alpha is again tan alpha, so our sigma will be now P max into 1 by cos alpha is secant alpha, so it becomes secant square alpha minus P dash tan square alpha. So this is the equation for principal stress in a gravity dam. Now equating the horizontal component of forces to 0, horizontal components to 0, due to sigma dr, the horizontal component is sine component. So sigma dr sine alpha, which is acting towards right, let us take it as positive, and towards left, let us take it as negative. Then this component will be P dash ds into cos alpha, which will be negative. So take this as positive, minus P dash ds cos alpha. Tau is acting towards left, so let us take it as negative, minus tau into dB is its component. Will be equating it to 0. Tau dB will be equal to sigma dr sine alpha minus P dash ds cos alpha. Dividing by dB, tau will be equal to sigma into dr by dB into sine alpha minus P dash into ds by dB into cos alpha. Substituting sigma value obtained before and dr by dB and ds by dB. dr by dB, dr is the adjacent side and dB is the hypotenuse. Adjacent by hypotenuse will be cos. So this is sigma, we obtained it as P max into secant square alpha minus P dash into tan square alpha into dr by dB is cos alpha, so cos alpha into sin alpha minus P dash into ds by dB. ds is opposite and dB is our hypotenuse. Opposite by hypotenuse will be sin alpha, so P dash into sin alpha into cos alpha, multiplying P max into secant square alpha into cos alpha into sin alpha minus P dash into tan square alpha, that is sin square alpha by cos square alpha into cos alpha sin alpha minus P dash into sin alpha cos alpha, which is equal to 1 cos gets cancelled, then sin by cos is tan alpha minus 1 cos gets cancelled, and then sin by cos will be tan alpha. Then taking P dash into sin alpha as common, then this will be sin square alpha as common, this will be sin alpha by cos alpha minus cos alpha by sin alpha. Minus of minus, it will become plus. Now tau will be equal to P max tan alpha minus P dash into, we took sin square alpha as common and taking LCM, this becomes sin square alpha plus cos square alpha. So that is sin square alpha plus cos square alpha by sin alpha cos alpha. One sin gets cancelled. Sin square alpha plus cos square alpha is 1. Sin by cos will be tan. So this is P max tan alpha minus P dash into tan alpha. Taking tan common, P max minus P dash into tan alpha. So our principal stress sigma is equal to P max into secant square alpha minus P dash into tan square alpha, and tau shear stress is P max minus P dash into tan alpha. If downstream side water is absent, then P dash will be equal to 0. Then principal stress will be P max secant square alpha and shear stress will be P max tan alpha. If no water on downstream side.